Hello and welcome to DataBasic, a Warwick Data Science Society podcast aimed at making data science simple and accessible by discussing the latest developments in the field. I'm Tim Hargreaves, a third-year maths stats student, and in this episode I'm joined by Eric Siegel, author of the popular data science book Predictive Analytics. On top of this, we'll have a short segment discussing the dangers of relying too heavily on Blackbox models in finance. But before we get to that, it's time to welcome our guest, Eric Siegel. Welcome to episode 2 of DataBasic. Today, I'm joined by Eric Siegel, author of the #1 Amazon category best-selling book, Predictive Analytics, and founder of the Predictive Analytics World conference series. Before we begin, I would like to point out how surreal this interview is for myself and undoubtedly many other passionate data scientists at the University of Warwick. This is because Eric's book, Predictive Analytics, is the primary introductory text for the data science degree course at the University of Warwick. It's incredible to go from reading his book just a few years ago to talking to the man himself. With that in mind, I'd like to welcome Eric to the podcast and thank him for offering his time to chat.
My pleasure. Thank you, Tim.
Okay, we'll kick off by asking some questions about your background and journey into data science before taking a deeper dive into the field in the second half of the interview. Now, most interviews begin by asking their guest what they do. Instead, with the world of data science experiencing such rapid growth and the hype that comes with it, it would be more interesting to know what your non-technical friends and family think you do and how that differs from reality.
There is a lot of misconception around analytics, machine learning, predictive analytics. In fact, the preface of the book you mentioned, I start off by saying people often look at me funny when I tell them what I do. It's a career hazard. The fact is, some people think that it's just reporting, sort of pulling together data. Some people think it's sort of intrusive data collection. Other people think it's incredible prediction that's just as accurate as a crystal ball. But, in a nutshell, predictive analytics, which is basically the same thing as machine learning, learns from data to make probabilistic predictions for each individual in order to more effectively target marketing, fraud detection, online ads, all kinds of operations that make more effective the mass scale functions of all kinds of organizations and companies and government agencies. But this is really more about the analysis of the data. What do we do with that data that's so valuable, and how do we get predictions from it? And the predictions themselves are not necessarily always accurate. What's important is predicting better than guessing. In many cases, you don't have a magic crystal ball. You're not predicting terribly accurately, but by predicting better than guessing, you do render these mass scale operations more effective.
That's brilliant. That notion of predicting only slightly better than guessing is an interesting one, and something we'll hopefully circle back to when we talk about ensemble models later. But for now, let's start from the beginning. Your academic background is centered around computer science before moving into broader predictive fields for your PhD. In what ways do you feel that studying computer science has prepared you for the sort of work that you do?
Computer science is kind of a funny field. It's sort of the amalgam of everything to do with computers as far as how you engineer better software, engineer better hardware, and how you design software to be more user-friendly. But then it also includes very abstract theoretical branch of mathematics called theoretical computer science. It's kind of like if you had a toaster science department at a university where it's all the culinary arts of a toaster and also how you engineer a better toaster. It's a bit arbitrary. They say that anything that has the word science in it isn't a real science, whereas like physics and chemistry, these are the real sciences. But the fact is, when you're in that area, you do learn a lot about algorithms, about some of the core math that's important behind machine learning, and then, of course, largely about programming. But these days, if you're in the field of analytics or machine learning, you don't necessarily need to be much of a hands-on coder. It depends on the role you're playing, the type of analytics you're doing, and whether you're on the research side and what kind of software you're using. There's the vast majority of machine learning methods already have existing software packages ready for you to use. So I think computer science for me has really been important as far as perspective. I mean, it's really the study of algorithms. Algorithm simply means a process, something that could be programmed into a computer. That's sort of an informal definition of it. But the idea of how do you conceive of and formalize these problem-solving methods, that's what machine learning really is leveraging, because it's how do you define a method that will learn from a limited number of examples. Even if you have millions of examples or hundreds of thousands, it's still a relatively limited number of examples from which to learn compared to the number of possible scenarios that could exist. So you're always performing induction. You're always generalizing from a limited number of examples. So the algorithms that do that are the core technology we're leveraging when we deploy predictive analytics and machine learning. And that's that's sort of the huge stunt, right? The giants on which whom's shoulders we're standing when we make use of this technology.
So based on that, would you suggest that if I were, say, a non-technical student who's interested in data science, that it would be more important for me to focus on learning the general ideas and methodologies than getting into the technical details of advanced programming and algorithms?
Yeah, that's a great question. Absolutely. I think it's the concepts that matter, the idea of how it's generalizing from data and what it means to validate a model, to try it out on unseen test cases, make sure it does well. So sort of what did it learn, and then validating exactly how well does it predict. These are the concepts that matter first and foremost, even if you are a hands-on coder. So your role in a machine learning project could go anywhere from, at the most extreme, programming from scratch an innovative machine learning method. And that's very unusual, because typically you want to leverage existing methods and then therefore the existing tools that already implement those methods. But then at the other end of the spectrum is very much a need for the business side and operationalization of predictive models. That is, how do the scores output by the models, the probabilities for each individual, actually get integrated into existing processes at the organization, changing business as usual in the targeting of marketing, of fraud investigation, in the determination of approvals for loan applications, all kinds of things done in insurance, political campaigns, government sectors. There's so many different places where this basic idea of rendering a prediction for each individual makes a huge impact. But actually doing the number crunching and deriving a predictive model that can produce those probabilities is only half the battle. In actuality, you need to then implement or deploy those scores. And that integration is not just a technical endeavor. It's very much an organizational endeavor, which requires executive approval, management understanding, and in fact, management. It needs to be managed. There's a whole business side to the deployment of this technology.
Great. So whilst we're on the topic of education and learning, history has shown that you're not afraid to use unorthodox means to spread the word of data science and educate others about the field. We can take as an example your rap video about predictive analytics performed under the alias Dr. Data, which we will definitely be linking in the show notes. Regarding this, in your opinion, what are some of the best ways to learn more about data science and predictive analytics, and what methods are currently being underutilized?
Well, yeah, I think that watching a rap music video, definitely the very best way to learn. But I'm being facetious. We had a lot of fun making the music video. The lyrics actually are genuinely instructive around the field, although you may be distracted by the visual, which depicts the social consequences of being this particular kind of nerd. But I think it kind of proves I'll do anything to try to educate on predictive analytics and machine learning. And in fact, in the Coursera 3-course series that we just launched, which is called Machine Learning for Everyone, we have embedded within there a brand new music video. It's a new, also educational rap on machine learning. And that 3-course series, which includes a total of 141 videos, this is sort of stuck in the middle there, is entirely accessible for free, like most courses on Coursera. If you go to machinelearning.courses, that you'll find out how to access it for free.
And you should be able to find that link in the show notes as well. We'll talk more about data science, predictive analytics, and your book on the topic in the second half of this episode. But for now, I would like to ask about your inspiration for writing the book, and how you feel now that it is a major introductory text for many data science courses across the globe.
Well, I wanted to write a book that anybody would understand, my non-technical uncle or anybody who might be interested in science, sort of from the pop science perspective. I wanted it to be that accessible, that relevant, that engaging. That was my goal in writing the thing, because from my perspective, machine learning is the most interesting kind of science. It's the coolest science. I mean, we're talking about a machine that automatically derives new insight. It draws generalizations from data. That concept of induction or generalization is a profound idea, and all sorts of fields and areas and industries can be improved and provided great value with this basic fundamental idea. And most of the algorithms that do it are quite generally applicable. And the thing that makes a difference of what problem they're solving and to which industry vertical they apply is simply which training data you provide to the algorithm. So to me, this stuff is great and everybody should know about it. And it's fun to sort of convey how it works. Whereas for sort of your typical person walking down the street, it sounds super arcane, but they know that the basics of chemistry and physics and what have you, they were taught this in high school or in grammar school or what have you. Should be applied just the same. So with that perspective, I thought, well, look, why not try to make this thing just as understandable and interesting to any reader as possible? Even though, of course, the vast majority of people who take an interest will either be the technical people interested in the field from a technology standpoint, or the business people who want to actually deploy it and gain value from it. So that was my basic goal.
And it definitely succeeds in that regard. It is a very accessible and interesting book. So I would definitely recommend it to any WDSS members listening to this podcast. Thank you, Eric. We'll be right back after this segment for a deeper discussion on ethics, risk, and the latest developments in the field of data science.
What do you think about when I say financial services and trading? A lot of people think Wolf of Wall Street, Leonardo DiCaprio with red eyes screaming buy orders down a 1980s telephone. And well, for much of the last half century, that wouldn't have been an inaccurate description of the investment bank securities businesses. But ever since the early 2000s, a new kind of finance professional has come to dominate the industry, the quantitative analyst, or quant for short. These are the so-called geeks of the finance world. Often from a mathematics background, they apply computational and statistical models to help price financial assets, like equities, otherwise called stocks, ETFs, options, and other financial derivatives, thus identifying asset prices that strongly diverge from theoretical prices, generating alpha, also known as excess returns. To put this idea into context, consider retail traders. These are regular people who might have never worked in a bank or even finished university. Through Trading 212, Robinhood, and other accessible online trading brokerage platforms, regular people are now empowered to trade real assets. Whereas traditional sales traders working in banks might study valuation models of companies and carefully place trades based on complex financial data in real time, retail traders instead might see a news article, perhaps a recent partnership between Oxford University and AstraZeneca, and without following any particular strategy or structured data pipeline, will place irrational bets about the direction an equity will swing to. These irrational orders have quantifiable effects on asset prices, pulling them away from their theoretical value. Now, if you're a quant, and you know C++, Python, you have an understanding of volatility services, and you know that an asset or a derivative of that asset, like an option, has a price which has swung away, has diverged from its theoretical value due to some irrationality in the market, then you can help make a market correction. You can bet in the opposite direction and help restore that asset price to its theoretical value or closer to it. That's a way of making money purely based off of the power of statistics and data. In recent years, quantitative traders have become central to front office teams in both investment banks and hedge funds. With this rise has come new data packages, APIs, and libraries easily accessible through Python that price assets in real time. It's easier than ever to build trading algorithms that generate returns consistently and reliably. Most importantly is the more recent implementation of Blackbox models. These are data pipelines that learn to price assets and even make trading decisions by learning from historical asset behavior. They're not manually modifiable. They're a black box, per se. Now, as you might imagine from the name black box, you actually can't see inside of a black box model. You can't see its inner workings, its cogs, its turning wheels. It takes in data, it draws conclusions, it develops strategies, and it gives you an output. Now, how the black box makes decisions, sometimes that's a mystery. But as models have become more sophisticated, the industry now faces a single, almost insurmountable challenge, a challenge of data quality. Most pricing data is highly unclean. It's cluttered with seasonal trends, abnormalities. During COVID-19, we've seen unprecedented liquidity interventions from the Federal Reserve. These are artificial market moves that have happened purely to keep industries afloat. Interventions from the government that swing an asset price away from where it should theoretically move to in a vacuum, in a free market system. Now, feeding this heavily unclean data into a black box pipeline is like training an animal to perform in a circus and then releasing it into the real world and expecting it to behave normally. And the problems don't stop there. You see, for every trade executed, algorithmic or otherwise, a trading venue must be chosen. Sometimes the optimum venue might be Frankfurt. Other times, it might be optimum to execute a trade via the London Exchange. Smart order routing algorithms are used in hedge funds and banks to automate this decision. Now, these algorithms are relatively straightforward to set up, but they require data from all trading venues or possible trading venues in real time. This is synchronous data from all around the world. And if data synchronicity sounds like a challenge, well, you'd certainly be right, because London and Frankfurt are actually 640 kilometers apart. Even at the speed of light, that's a 2 millisecond delay between venues. And of course, in real life, data signals move much more slowly than the speed of light. Realistically, algorithms requiring a full execution time of 35 milliseconds have an entirely different view of the market and make decisions based on an entirely different view of the market compared to another requiring 70 milliseconds. Your data pipeline is everything. In fact, depending on your spatial separation from trading venues, from exchanges, your view of the market is entirely different. Two completely identical algorithms operating in different places will behave differently. To that extent, some might argue, is there such a thing as a real snapshot of the market? Next, consider how algorithmic trading strategies work. Many of them are set up based on a volume-weighted moving average profile. They try to make trading decisions while also considering how much a particular asset is being publicly traded in an exchange. An equity might look very profitable, but if nobody else is interested, then that's quite suspicious. However, a volume-weighted moving average is a cumulative calculation. With every new data point is a new calculation. For that reason, with new data comes more lag. And depending on your data pipeline, depending on your technology, your decisions will be completely different. And so regardless of the sophistication of your black box model, if your data is poor, so will be your output. And that's not to say that the industry uses poor data. Platforms like Goldman Sachs Marquee have become popular recently, which offer premium datasets on assets around the world. But considering that data will always be flawed, it's important to recognize that even the best black box pipelines will always fall a little short of perfection. So what does this all mean? Well, in summary, recent decades have seen the securities and trading industry shift from adrenaline-fueled shouting matches to Python, to black boxes, but it's now far too easy to assume that the biggest challenge is building your model, your pricing model, your algorithm. Well, no, instead the challenge is understanding and accepting the sometimes scientific limits of your data. Nobody has a monopoly on information. The laws of physics have seen to that. And if the quant industry continues to grow, let's pray this growth is followed by a greater investment into data quality management, cleaning, and latency reduction. Otherwise, it might not just be those retail traders swinging asset prices in the wrong direction. It might actually be the biggest banks, the biggest hedge funds, and the biggest Oxbridge-filled trading firms in the world that cause the market to go awry.
Welcome back to our interview with Eric Siegel. It's time to address the elephant in the room, predictive analytics. So Eric, you've already talked a bit about what predictive analytics is, but how exactly does it differ from data science at large?
Well, data science as a general field is not a well-defined field. It's sort of a broad subjective area, which basically means, hey, let's do something smart with data. It certainly includes machine learning and predictive analytics under its sort of broad umbrella, but maybe the best way to define data science, since it's not any particular technology, method, approach, or value proposition, it's really a culture of smart people trying to figure out how to make value out of data. Whereas machine learning, predictive analytics is a well-defined field, in a nutshell, learning from data to derive predictions for each individual.
So in your book, Predictive Analytics, you highlight how predictive models can be used to lower risk and make safer decisions. Does this still hold when the underlying assumptions and historic trends of our model are violated? For example, due to a global pandemic, say? And if not, how do we best prevent this sort of model drift?
Well, we can't prevent too much model drift, which is goes back to the reason we're doing data analysis in the first place. The value proposition of data-driven decisions is only increased by how rapidly the world's now changing due to the pandemic. We don't know exactly how to characterize the changes unless we look at the data. So we do have model drift. That is to say that the model's performance degrades over time because the world has changed. It's now different from it was at the time the original training data had been collected. So now we refresh it. We gather new updated training data and generate typically a brand new model. You can incrementally improve a model over new data, but in almost all cases, what you actually do each time is you push the go button, and from scratch, the algorithm, the computer derives a brand new model from the new, more updated, more recent training data. So because of that cycle, nothing qualitative about that cycle changes now, but since the world's changing more rapidly, people will probably be doing that update more frequently.
Yeah, that's quite a nice way of looking at things, seeing the changing world not only as a problem to overcome, but as a learning point to update our beliefs. So whilst we're talking about your book, one of the latter chapters discusses the use of ensemble models for supercharging prediction. At the time of writing, you described the technique as something new even to many seniors, although it's clear that a lot has changed since then. What are some of the use cases of ensemble models that you have since become aware of that excite you the most?
So think about an ensemble model where basically you take a bunch of relatively simple models. It could be decision trees or logistic regression, and then you have them all either kind of vote or somehow bring together all those predictions, and often in a relatively simple way. Is that it's a really elegant way to supercharge the predictive model's effectiveness without an incredible amount of complexity. So deep learning is a very complex modeling method. And, the upside are all the incredible performance capabilities I just mentioned, but the downside is the complexity both in the user, so the analytics expert who's actually applying deep learning needs to be that much more advanced, that much more expertise. And then the resulting model can sort of be this soup of math. It's very opaque. It's kind of a black box rather than a transparent box. It's hard to understand what it's doing, what's going on in there. Whereas you can kind of sidestep the need to get quite that complex especially if you're applying machine learning to traditional business problems by using an ensemble method. And I would say that, there's a lot more knowledge about this area pervasive across the field of machine learning than there was when I wrote the first edition of the book. And it's a pretty regularly used thing. So, many Kaggle and other public data mining or data science competitions actually use ensemble models. And even the sort of first big famous machine learning competition, which was Netflix movie recommendations, where they the winner got $1 million. It was a group of people for creating a predictive model that was 10% better than their existing system at the time. The winners very much leveraged ensemble models, and in particular used them in order for teams of competitors to team up and become sort of Uber or meta teams. So if you had, let's say, 2 teams and they each had a model, well, they could combine those models and kind of get the best of both worlds by ensembling them together.
Yeah, your comment about the use of ensemble models for machine learning competition sites like Kaggle is definitely something that I've seen. It's amazing to notice how far up you can get up these leaderboards with just a simple ensemble model tuned in the right way. So it would be nice to wrap up with something simple and easy, but instead I have a question about the ethics of machine learning, so apologies for that. So there often seems to be a complicated dichotomy between creating both performant models and respecting a user's privacy. Are there any ways that we could better align incentives to try and mitigate these issues?
That's a great question. So first and foremost, taking a little bit of a step back, the ethical issues that come up with machine learning include what you mentioned, which is that there's data privacy issues. And if you're using machine learning, then you're going to automatically want to have more and more data accessible and aggregated, right? So it puts your incentives automatically in a way that opposes privacy. And I would say in general, as far as privacy, what we want is for consumers to be informed of what data is being collected and have the ability to opt out about as far as what data is being both collected and aggregated. But other ethical issues that really stand out include what's the output. So what we're talking about there was the input, but what's the output of the model? What's it predicting, right? Is it predicting something sensitive, like whether you're going to quit your job, whether you're pregnant? There was a famous story in 2012, United States retailer Target predicting which customers were pregnant. Whether you're going to commit a crime, what your ethnic group is, and there's been a bunch of studies showing the ability to effectively predict ethnic group based on, for example, Facebook likes. We see that China is predicting ethnicity specifically for purposes of discriminatory treatment of the Uyghurs, an ethnic group in China. And then I'll say one other broad area is what people often refer to as machine bias. So this is another area, another ethical concern where you have a model that's predicting something consequential. It's driving decisions that make a big difference in individual consumers' lives, such as whether you're going to get access to a loan, whether you're going to get a job or housing, and whether you're going to stay in prison. And it turns out that these models, even if they do not take a protected class such as race as direct input, still have a differential treatment between racial groups, such as differing false positive rates. So there's a whole plethora of ethical concerns and issues. I've been writing a bunch about these things. I had a chapter in the book. It's one of the upfront chapters, chapter 2, on some of these issues. And since then, I've been continuing to write op-eds, such as in the San Francisco Chronicle and Scientific American blog. My op-eds list of about 11 articles so far can be found at civilrightsdata.com.
Brilliant. Thank you for such a comprehensive answer. We'll definitely make sure the links to those op-eds are in the show notes. It's been great talking, but unfortunately that's all we have time for. So thank you, Eric, for sharing your excellent insight. It's been amazing to talk to someone so clued in on both the theoretical and practical sides of data science.
Thank you, Tim. Great talking to you.
Now, before you go, where can people keep up to date with your latest work and projects?
Yeah, well, go to machinelearning.courses. There you'll see how to get free access to our brand new 3-course series on Coursera, which very much delves both into the business side, ethics side, and technical side of machine learning. There you'll also see my bio, which has links to the civil liberties and ethics op-eds and other areas of my activity, the book, Predictive Analytics, and our conference series, Predictive Analytics World.
Great. Once again, thank you, Eric, and thank you, everyone, for listening. Next time, we'll be joined by Shikhar Dev, an AutoML researcher at Delft University of Technology. We'll be talking about automated machine learning, its successes, its flaws, and the ethical complications that come with its use. Don't forget to subscribe to our YouTube channel and follow us on Facebook, LinkedIn, and Instagram to keep up to date on the podcast and the society. Thank you for listening, and we'll see you next time.